Okay. One diagram was till nitrogen, and till nitrogen diagram was this. This was sigma 1s, this is sigma 1s star, this is sigma 2s, this is sigma 2s star, this is pi 2px, this is pi 2py, this is sigma 2pz, this is pi star 2px, this is pi star 2py, this is sigma star 2pz. Now this is the diagram which we use up to nitrogen, and here sp mixing takes place. Okay. Then we have another diagram. Here and here. This is sigma 1s, this is 1s star, 2s, 2s star, 2pz, 2px, 2py, star 2px, star 2py, star 2pz. Here O2, F2, Ne2, and here sp mixing. You may say not effective, or you may even consider does not take place. So that is what we have as sp mixing not taking place, and this is what we have as a diagram. Now these diagrams are supposed to accommodate the electrons. Now when we fill the electrons, the way of filling the electrons is like this. The first electron we are going to fill here, the first electron. The second electron here with the opposite spin. Here would be the third electron, here would be the fourth electron. 5, 6, 7, 8. And now be very clear. 9 and 10. The two electrons are going to be in different orbitals having the same energy. Can you see Rohan?
Yes, sir.
9, 10. And then we are going to have 11, 12.
Okay.
Here we are going to have 13, 14. We may have 15, 16 here, but then beyond that we should be using this diagram. So here the diagram would be again 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then again we are going to have 13, 14. Then we
Sir,
have,
I can't see the bottom of the board for the second diagram.
is it now visible?
No, sir.
Now?
Little more, sir. I can't see the bottom.
Now is it
Ah,
okay?
yes, sir.
Okay. Then we have 15, 16, 17, 18, 19, 20. Now these electrons, they are going to be represented like this. You are not going to write the numbers, you are going to write the electrons. And electrons, you are going to write it like this way and this way. So you can consider that except for these, the odd number are going to be like this, the even number are going to be like this.
Yes, sir.
Okay. So you are just going to fill it, whatever is the number of electron. So if we are going to make the diagram, then in that case, we are going to talk about any species that is given to you. You are going to talk about how many electrons, total number of electrons it has, and just fill them up.
Yeah.
Okay. Now, this can be written as a way, like you can write it something like this way. You can write this way. We had in the atomic structure, we had made the 1s2, 2s2, 2p6, 3s2, 3p6 like that. In the same manner here also we can write it like we can write sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Then we can have, if you talk about without sp mixing, with sp mixing, we are going to have pi 2px, pi 2py. Then we have sigma 2pz. Then we have pi star 2px, pi star 2py. And then we have sigma star 2pz. Now this is the diagram, or this is the order with sp mixing. When sp mixing does not take place, the order is going to be sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. We have sigma 2pz, and then we have pi 2px, pi 2py, pi star 2px, pi star 2py, and sigma star 2pz. So here it is, sp mixing does not take place.
So the first and second one, the only difference is that this sigma 2pz has shifted to the
Yeah, that's the
left.
only difference here. This is the part which is different.
Yeah.
Other than that, everything else is same.
Yes, sir. Yes, sir.
Clear. So that is what we have as the sp mixing does not take place and sp mixing takes place. These are the two diagrams. Now what you are going to do is you are going to make some diagrams. And in making those diagrams, these are going to be something like H2, H2 plus, H2 minus, He2, He2 plus, Be2, not Be2. First would be Li2, Li2 plus, Li2 minus, Be2, Be2 plus, Be2 minus, let's say. Then we have B2. I forget B2 minus. B2, B2 plus, B2 minus, B2 minus minus. We have C2, C2 plus, C2 minus, C2 minus minus. N2, N2 plus, N2 minus, O2, O2 plus, O2 minus, O2 minus minus. F2, F2 plus, F2 minus, Ne2, Ne2 plus. Now, when you are going to do this question in FitG, they are going to give you certain other compounds as well, and those would be Cn, Cn plus, Cn minus, NO, NO plus, NO minus, CO, CO plus, CO minus. Now you are going to make these diagrams. Now what exactly you are going to do in it? What you are going to do is you are going to find something like bond order. Bond order is equal to bonding electrons minus anti-bonding electrons divided by 2. That will be the bond order.
Yes, sir.
Okay, so that will be the bond order. Now once you have got the bond order, remember, higher the bond order, more is the bond strength. More is the bond strength, shorter is the bond. Shorter is the bond, more is the bond energy. So more is the bond order, more is the bond strength, more is the bond energy, and shorter is the bond. Is it clear? Clear?
Yes, sir.
Now here further, you can tell me whether it is paramagnetic or diamagnetic.
Sir, what is paramagnetic?
I think we discussed that. The species which contain unpaired electrons are termed paramagnetic.
Yeah. Yeah.
The species which contain all electrons paired up are diamagnetic.
Yes, sir.
Okay, so we have talked about paramagnetic and diamagnetic substances. And then we have, this is what we are going to find. Now, bond order can be positive. It can turn out to be negative. It can turn out to be fractional, and it can turn out to be zero. The species which contain zero or negative bond order simply do not exist. Is it clear?
Yes, sir.
Okay. So, Rohan, what I'm going to do is I'll just fill up the electrons for nitrogen.
Fine.
Okay. So what I'm going to do is, yeah, here now I'm not going to write 1, 2, 3, 4. But my counting will go in this manner only. So when I fill the electrons for nitrogen, it's going to be filled in this manner. Nitrogen is 7 atomic number. It has 14 electrons. So I'm going to fill 14 electrons here. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is how I'm going to fill the electrons in nitrogen. Okay?
Yes, sir.
Okay. Now let's find out the bond order of nitrogen. How many bonding electrons? Bonding electrons are the ones which do not have the star with them. Like it becomes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the bonding electron come out to be 10. Talking about anti-bonding electrons. Anti-bonding electrons, we have the electrons with star. 1, 2, 3, and 4. So there are 4 anti-bonding electrons divided by 2. So this becomes equal to 6 by 2 equal to 3. So bond order of nitrogen is 3.
Yes,
And
sir.
as you can very well see, all the electrons are paired up. This is diamagnetic.
Yes, sir.
Okay.
Yeah.
So start making the diagrams of all these species which I have given you.
So do you have to make these the diagrams one by one?
I think you should. It won't take
Fine.
much of the time.
Yeah.
Okay. And once you have made a few of them, we are going to discuss something and then we can make further.
Yes, sir. So H2 is the bond order is 1 and it's diamagnetic, right?
Yes, it is.
Okay. Sir, after H2 minus, what is there? I'm not able to see the compounds
He2.
properly.
He2.
Okay.
And hold on. If you have made H2 minus, then in that case you would find that H2 minus also has a bond order of 0.5
Yes, sir.
and H2 plus also has a 0.5
So minus 0.5, right?
plus 0.5
Okay,
H2.
okay. Yes, sir. 0.5.
Since H2 minus and H2 plus both have 0.5 bond order, it is actually H2 plus which is more stable. And the reason for H2 plus being more stable is that it has less number of anti-bonding electrons. So just write it down.
Yes, sir.
If two species have same bond order, if the two species have same bond order, then the species which has less number of antibonding electrons, the species which has less number of antibonding electrons is more stable.
So the bonding electrons are the ones which are on the non-star ones.
Yes.
Okay. So then for He2 it shouldn't exist.
Yes, it doesn't.
Okay. So in B2 we have one electron in 2p in pi 2px and one in pi 2py.
B2, yes.
So will
And
that make it diamagnetic or
it's
paramagnetic?
paramagnetic because two unpaired electrons are there.
Okay. Sir, B2 minus the bond order is
1.5.
okay.
You can see it is not necessary that minus is going to have a lower bond order. It might be having a higher bond order.
Okay.
Clear? So there was possibility that B2 minus has a higher bond order because it has having an electron in bonding orbital.
Yes, sir.
Which one you are on, Rohan?
Sir, done, sir.
Which
I
one?
finished C2 plus. I
Mm-hmm.
don't know how to do CN.
You don't know how to do
CN, sir.
CN.
Yeah.
Simply use the nitrogen one.
So what?
Use the nitrogen diagram.
Yeah.
Use this
So,
diagram
sir,
for all these.
yeah. So then we add the carbon
And
electrons and nitrogen
yes.
electrons. Okay. Yes, sir. Done.
Okay, so let's see what is O2.
Okay.
O2 is paramagnetic or diamagnetic?
One sec. Sir, paramagnetic.
Yes, O2 is paramagnetic. Now let's consider something like C2.
Okay. Sir, diamagnetic.
What is the bond order?
Two.
Bond order is 2.
Yes, sir.
How many sigma, how many pi?
Um, Sir, 8 sigma, 4 pi.
Now, if I talk about this sigma, they cancel out. This is bonding, this is anti-bonding, they cancel out.
Okay.
This is bonding, this is anti-bonding, they cancel out. And this becomes the diagram of carbon.
Yes, sir.
So carbon has only 2 pi bonds, it doesn't have a sigma bond.
Yeah.
Is it okay? C2 has only 2 pi bonds, it doesn't have a sigma bond.
Yes, sir.
Is this clear?
Yeah.
So that is what we have as the molecular orbital theory.
Okay.
Anything anywhere you want to ask?
Nothing, sir.
Okay, so today we have the class till 7:30.
Yeah.
Okay, so let's get a little further and we are now going to talk about something called the dipole moment.
Sir, I'll use the document come.
Sure, sure.
Yes, sir. Hello.
Okay, Rohan. So what we are doing now is called the dipole moment. Now, before we get along with the dipole moment, let's understand the word called polarization. When I talk about the word polarization, this word is used in many places. Basically, whenever we have a high concentration of anything at any place, we term it as a pole and we term it as a polarization. So just write the definition of polarization. Creation of creation of opposing concentrations or creation of opposing concentrated regions creation of opposing concentrated regions in what should be what should be a uniform distribution in what should be a uniform distribution is termed polarization polarization. Full stop. These regions these regions of high concentration these regions of high concentration are termed are termed poles. These regions of high concentration are termed poles.
Yes, sir.
Okay, so that's what we call as polarization. Now, having talked about what the polarization poles are, we have many kind of poles. Now, right further,
Yeah.
these poles always exist. These poles always exist in pairs. These poles always exist in pairs. Now, what does it mean? It simply means that when we talk about these poles, we are going to get dipole, we can get quadrupole, we can get octapole, but we are not going to get pentapole.
Yes, sir.
Okay, so they will always exist as pairs. Okay, now we can have so many poles. We can have magnetic dipole, we can have electric dipole, we can have geographical dipole, we can have the Cold War like power dipoles, and we can have so many dipoles. But what we are mainly concerned with is the electric dipole.
Sir, 1 second. Just, yes, sir.
Yeah. So we are going to talk about something called electric dipole. Write the definition. Two equal, two equal and opposite charges. Two equal and opposite charges separated by two equal and opposite charges separated by a small distance. Two equal and opposite charges separated by a small distance constitute constitute electric dipole.
Yes, sir.
Okay, that's what we mean as electric dipole. Okay. Now, right further, the distance is small. The distance is small in comparison to the distance is small in comparison to the distance of the point of observation. The point of observation from the dipole. Okay.
Yes, sir.
Fine. That's what we have as a dipole. So what we are going to say, electric dipole is going to have a positive charge here. It's going to have a negative charge here. It is separated by a small distance. This distance, it is r. So that is what we call as an electric dipole. Now, having talked about this electric dipole, now we are going to talk about what the electric dipole would be in case of chemistry. If we talk about something like chemistry here, let us say we have a molecule A, B. When I say a molecule A, B, then there are two possibilities. One possibility would be that A and B are identical. If A and B are identical, then in that case, this A and B are going to have exactly the same electronegativity. None of them is going to pull the electron. The electron is going to be right in the center. No charge separation, and this is not going to have any kind of charge separation or concentration regions. This is not going to be a dipole. But if A and B are not identical, if A and B are different, then in that case, there is a possibility that this B or A are going to pull the electrons more strongly than the other atom. Let us say B is more electronegative. Then B is going to pull the electron towards itself, and B is going to get a delta negative charge while A is going to get a delta positive charge. Now this is going to create a small negative and a small positive which are equal and opposite, and they are separated by a small distance. Now this is what we can term as a dipole. So whenever the two different atoms join together, they create a dipole. Is it okay? So here we are going to
Yes.
talk about in chemistry. Now, whenever we talk about the dipole, we talk about something called the strength of the dipole. The strength of the dipole is measured in terms of dipole moment. The strength of the dipole is measured as the dipole moment. Now, when you talk about the dipole moment, this has a peculiar way. It is represented by a symbol mu. Now, this mu is equal to the magnitude of charge separation multiplied by the r. Now, the problem is if I simply say the distance, you very well know that distance can be misleading. We could have a huge distance, we could have a very small distance depending on the path that the body follows. So the distance depends on path. So it would be quite obvious that rather than using the word distance, we are going to use the word displacement. So it becomes charge separation multiplied by displacement. So this is charge separation multiplied by the displacement.
Yes, sir.
Is it clear?
Yeah.
Okay. So displacement is a vector. So this charge is a scalar quantity. R is a vector quantity. So scalar multiplied by a vector is also going to give us a vector.
Yes, sir.
Clear? So this mu is a vector quantity. Fine.
Yes, sir.
Now, let us understand the direction of the dipole moment. If it's a vector quantity, I need to give it a direction as well. So when we understand what the direction of the dipole moment would be, I need to see where the charge is being displaced. In chemistry, we are going to talk about the displacement of the electron. If I talk about the displacement of the electron, it's quite obvious that the electron is going to move from the species which is less electronegative to the species which is more electronegative. That is, it's going to move from the final positive to the final negative. So, in chemistry, the direction of the dipole moment is from positive towards negative. Is that clear?
Yes, sir.
Further, if I talk about this, I need to have some dimensions also, magnitude also.
Yeah.
I think it's not a big thing to understand that the dipole moment is simply going to have the dimensions of charge multiplied by the dimension of displacement.
Yes, sir.
So what do you think would be the SI unit of dipole moment?
Sir, meters.
Meters with unit of charge.
Yes. Yeah.
Coulomb
Oh, yeah,
meter.
yeah.
So Coulomb meter is the SI unit of dipole moment. Clear? Okay. Rohan, we are going to continue it in the next class.
Okay.
Okay then.
Yes, sir.
Good night.
Good night, sir.